Welcome, and thank you for joining. In an era where digital advertising fuels over $600 billion in global spending, companies like Google, Meta, Amazon, and ByteDance are racing to optimize ad performance at massive scale. Recently, Meta revealed that improvements in real-time ad analytics contributed to a 12% increase in click-through rates, CTR, across its platform, driven by better aggregation and filtering of click events. Similarly, Google Ads announced advancements in live campaign insights, powered by stream processing at petabyte scale. In this session, we'll explore how to design a real-time ad click event aggregation system that can operate at the scale of Facebook or Google. This system must handle billions of events per day, support low-latency queries, and be scalable, fault-tolerant, and highly efficient. We'll walk through the problem statement and core requirements, architectural choices and design trade-offs, real-time and batch processing, Lambda architecture, techniques for scaling, deduplication, and fault tolerance. By the end, you'll gain practical insight into building a production-grade data pipeline capable of powering modern digital ad platforms in a hyper-competitive market. The problem is to design an event aggregation system for real-time ad clicks for Facebook or Google. We need to aggregate clicks on ad level in the last M minutes and support top K and aggregation filtering by different attributes. Here are some good requirement questions to ask. What's the format of the input data? What's the data volume? What are some of the most important queries to support? What's the latency requirement? In this slide, we present the high-level architecture for a real-time event aggregation system tailored for tracking and analyzing ad clicks. This system is designed to handle extremely high volumes of click events efficiently and to support both raw data storage for auditing and flexible querying for analytics. Let's start with the query APIs. We expose two primary GET endpoints. The first retrieves the aggregate number of clicks for a given ad ID over a recent sliding window, say the last M minutes. This supports real-time dashboards and alerting. The second API fetches the top K most clicked ads in the same time window, useful for dynamic ranking and performance monitoring. Moving to the data model, we maintain two types of data: raw click events, which include fields like ad ID, timestamp, user ID, IP, and location. These are valuable for offline analysis, compliance, and reprocessing. Aggregated click data, with entries like ad ID, click minute, and count. This pre-aggregated format supports low-latency querying. We store raw data in scalable stores such as Cassandra for fast writes, or S3, encoded efficiently with formats like Parquet or Avro for analytical workflows. To scale processing, we adopt asynchronous architecture. A message queue, like Kafka, acts as a buffer between click producers, e.g., logging infrastructure, and consumers. A log watcher continuously writes click data into the queue, ensuring reliable ingestion even during spikes. For processing, we use a MapReduce style aggregation pipeline. The map nodes consume raw click events from the queue, perform cleaning, filtering, and transformation. The aggregation nodes, a form of early reducer, bucket and count clicks by ad ID at the granularity of each minute. Finally, the reduce nodes combine partial counts from aggregators to produce the final output, which gets stored in the aggregated table. This design supports both real-time querying and long-term analysis, and is extensible for filtering, e.g., by campaign or region, deduplication, or fraud detection later on. In this design deep dive, we'll explore how a large-scale event aggregation system handles real-time ad click data efficiently, with strong delivery guarantees and scalability. We start by supporting both streaming and batching, a classic Lambda architecture. Streaming enables low-latency processing of click events as they arrive, ideal for real-time dashboards or alerting. Meanwhile, Batch processing handles backfills or historical analysis, using systems like Hadoop to re-aggregate data from raw logs stored in S3 or Cassandra. To support data recalculation, we run a dedicated recalculation pipeline. This isolates historical correction jobs from the real-time path, protecting latency-sensitive components. Re-aggregated results are published to a second message queue and used to update the serving layer asynchronously. Timestamping is critical. We distinguish between event time, when the click actually occurred, and processing time, when it's processed. To handle delayed data, we use watermarking, which delays aggregation just enough to include most late-arriving events without stalling freshness. We implement various aggregation windows to support different use cases: tumbling windows for fixed-interval reporting, sliding windows for continuous metrics, hopping windows for overlapping analysis, session windows for user behavior insights. Delivery guarantees aim for exactly once semantics, which is complex. We achieve this through deduplication at multiple stages: client-side, using IDs or timestamps, and server-side, via idempotent writes and offset tracking. Faults can occur anywhere, so deduplication logic is essential. To scale the system, we use partitioned message queues with brokers, producers, and consumers. Aggregation workers are split into mappers and reducers, and consistent hashing helps distribute writes evenly across database nodes. For hotspots, such as popular ads, we scale reducers horizontally. We maintain fault tolerance by checkpointing system state, like Kafka offsets, intermediate aggregates, and batch jobs. This lets us resume after failure without full reprocessing. Finally, we implement continuous monitoring to watch system health. Latency tracking ensures results are fresh. Queue depth signals processing lag. Reconciliation processes compare raw and aggregated data for discrepancies, ensuring integrity. This design ensures we can ingest billions of ad clicks daily, aggregate them in near real time, and serve analytics with high accuracy and fault tolerance.